So we embarked on that with Frédéric Lestrade, who was doing his PhD with me at this time. And we tried to prepare a very simple starting material, such as this one, starting from this tosyl acetal. And we did, of course, a very, very, very simple chemistry with iodophenol. We obtained easily this compound. And the halogen exchange took place nicely with a large excess of butyl lithium at low temperature. And you see that not only the exchange is taking place and the carbometallation taking place, but also the elimination and re-aromatization of the compound. So we got the expected cyclization, but the alene was not obtained, and instead we observed directly the benzofurane in relatively good yield and full control of the lateral double bond. So that was an interesting case, and we thought maybe we can take advantage of that, because we also noticed that we could take advantage of the triple bond with a milder base, such as KHMDS in this case, and we could force the isomerization of the triple bond into the alene. And then the cyclization would also take place on the central carbon of the alene in this case. And you can see that, of course, the molecule is the same. The yield is exactly the same, but the stereoselectivity is not as good. It's a little bit less selective. And it makes sense because in this case, probably the elimination went through this CSP2 vinyl lithium intermediate, while in this case, if you get this carbometallation, you would end up with a CSP3, so it's a beta elimination, regular beta elimination. So maybe that explains why the selectivity is not exactly the same. So we tried to extend that to other heterocycle and check if it was a relatively general method or not. So we did that with this iodohydroxypyridine by just grafting this acetal moiety. We obtained this propargylic compound and did the iodine exchange, iodine lithium exchange, and of course the cyclization, by chance the cyclization took place, and we were very nicely rewarded to obtain directly the expected heterocycle in a medium yield, but with a full control of the double bond. So that was pleasing. When we tried to extend that to other isomers, such for instance furo-2,3-C pyridines, starting from this hydroxypyridine, we prepared easily this compound. And in this case, we were disappointed because, as you can see, the cyclization took place in this condition, but not only. There was also isomerization of the triple bond into the alene, and this one-to-one mixture was impossible to separate because these two compounds have exactly the same elution by TLC and column chromatography. So that was quite disappointing. Fortunately, we noticed that the reason is probably that when we do the iodine lithium exchange, there is also now these protons that can be abstracted, and this leads directly to the alene. And probably that's the reason why we obtain this alene instead of that's the basic character instead of the nucleophilic character that is exerted. Fortunately, we noticed that by doing the pre-isomerization of the triple bond, as I showed before, using a mild base such as potassium terbutoxide, we obtained the corresponding alene, and this alene now was undergoing very nicely, well, not very nicely, in medium yield, the expected compound with a still acceptable control of the double bond. So this was an alternative solution to cyclization that would be a problem. We could extend that to many heterocycles. For instance, the synthesis of indole by this way is quite easy. You see that starting from these protected anilines, iodoanilene, we can just add always the same propargylic acetal, get this compound, and pre-isomerize it in this case, because the direct cyclization does not work, pre-isomerize it in alene, and do the cyclization on the alene, and obtain the corresponding indole in good yield, but moderate stereoselectivity in this case. The reason why this reaction is probably more difficult in this case is that with the Boc group that is necessary on the nitrogen, you probably have a stabilization of this intermediate aryl lithium. And as you can see in this case, this conformation is not very good for the cyclization to take place because the triple bond is staying very far away from the nucleophilic center. We could also extend that to aza-indole synthesis using aminopyridine such as this one, and always using the same time of chemistry, doing the same isomerization, then cyclization. We could prepare very good yield and decent selectivity, the corresponding aza indole easily. It also applies to 5-membered rings, not only 6-membered rings, but also 5-membered rings, such as for the synthesis of thienopyrrole of this type, starting from these thiophenes and by very simple steps converting them to these allenes and doing the cyclization in this way to obtain these compounds with a relatively modest control of the stereoselectivity. Unfortunately, we went through a big problem rapidly when we tried to extend this chemistry, because you have noticed that in all the cases I showed you until now, there was always a terminal acetal group on the propargyl position. If we next try to change that and replace it by any group, such as a methyl, for instance, a very simple one. So we did this chemistry, Mitsunobu condensation of this commercially available alcohol and iodophenol, prepared this compound, and did the iodine-lithium exchange with tertiobutyl lithium. What we were expecting, of course, was the same carbonylation to obtain this type of compound, and after quench, get the corresponding dihydrobenzofurane. Actually, did not take place at all. What we observed was the very uninteresting reaction. The lithium exchange took place, but no cyclization, either hydrolysis product or isomerization product, no cyclization at all. So it looked like the acetal was playing a major role in this chemistry, unexpectedly, actually. So that led us with Annelise Girard to take a closer look to this reaction and examine what was going on. You probably remember that in all the cases I have showed you, we were using a large excess of butyl lithium. So we wonder, why do we need such a large excess of base? This reaction normally would need only one equivalent, right? So we decided to have a look at what happened with one equivalent of butyl lithium. Very careful work. Let's do the things cleanly and check what is going on. So we did that. And what happened was very surprising, actually, because we observed this intermediate, probably, because after quenched, we got either with water or deuteroethanol, we get this type of compound. So you would mean, what is surprising in that? Well, what is surprising is the stereochemistry of this double bond, because this corresponds to an anti-carbolyation of a triple bond, and this has never been observed before. There is no anti-carbolyation of triple bonds in literature. So that was quite unexpected. Why would this lithium be on this position and not on this side? That was quite unexpected. So 2 questions, why? And second question, no beta elimination of lithium hydroxide in this case. Why? Why did we recover the acetal and not the elimination product as expected? So we tried to answer these 2 questions, and we did a theoretical study with Catherine Fersignier, who is an associate professor with me in Rouen. And Catherine Fersignier is a good specialist of theoretical calculation. So she did the DFT study on this problem.